The only thing that I'm going to say before handing over to Ovidio Andronesi, our own Dr. Andronesi, to introduce our speaker today, is that we are grateful to receive support from the P41 funded Center for Mesoscale Imaging housed at Martinos. With that, Ovidio, I'll hand it over to you to introduce our speaker. And again, thank you very much for being here with us today. Sorry, Ovidio, if you could speak from here so that people on Zoom can hear you. Thank you. Oh, and I choose just more.
Yeah, so it is my pleasure to introduce, invite today Professor Dr. John Shah, who is the director of Institute for Neuroscience and faculty, has a dual professorship at the Faculty of Medicine and Faculty of Natural Science at University of Aachen. Dr. Shah is leading a multidisciplinary team at Jülich in a research center where he develops ultra-high field MRI methods, imaging methods, and hybrid and simultaneous MR-PET. And he's here to present today about one of his latest innovation with a PET insert for human brain imaging at 7 Tesla. Thank you so much for coming, and we are looking forward for your presentation.
Thank you very much, and thank you all for coming also. I feel like a bit of an imposter here talking about PET, because PET's not really my speciality. I'm from the MR side, but since it's an MR-PET device, obviously we have to work very closely with both sides. And I'm going to begin with MRI, obviously. Okay. Just a quick overview of my institute. We have MRI. I had that. PET, Christoph Lerscher. We have two clinicians, brain tumor group and multimodal clinical imaging. And then we have a neuroimaging data science group. So I'd like to begin by my overall aim. And this is actually a figure that many people asked me for, including Siemens. I start by asking, why are we looking up the wrong end of the telescope with MRI? We start with structural changes because we can do that. It's very easy. Then we venture into fMRI because we can do that too, last 30 years or so. And then we start scratching our heads and thinking, oh, metabolic imaging, and that's been the focus of this conference workshop over the last few days, and we're pretty good at that too. And then when it comes to proteomics, genetic defects, we're lost. But if you look at a typical disease, typical dysfunction, it might begin with a genetic defect, think Alzheimer's, leads to a protein malformation, which at some point has metabolic consequences, and then functional changes. And finally, we see it in structural changes. And so I proposed this scheme here. We nearly got it through. Actually, we got the best score for in terms of science in the German so-called roadmap program to build a 14 Tesla. But unfortunately, politics got in the way, and we didn't get the 200 million that we were asking for. Shame, but we had the best scientific score. Helps me to sleep at night, knowing that the science was good. So we wanted to create a big database by doing ultra-high field MR-PET, entry level 7 Tesla, advanced level 9.4 Tesla, and future 14 Tesla, and then getting blood samples and DNA samples and so on. So I just wanted to give you an overall view of where I'm trying to head, and now you'll see where all the other parts fit in. I think we know this very well here. Multimodal, multidimensional imaging, MRI, structural, functional, blood flow, glucose metabolism we've seen today as well. Amino acid transport, that's the domain of PET really. Proliferation of tumors. Receptor density, we can't get anywhere near it with MRI. That's where PET is the gold standard. And if you want to look at drugs that are labeled, PET is your technique to go to. And then we come to MRS, chemical shift imaging. We can look at tissue pH, hypoxia, and about 12, 13 metabolites that we've seen. And on the left-hand side of the screen, you'll see a scale, spatial scale. We are now going towards sub-millimeter with MRI. And I'd like to convince you today we're going into the millimeter range with PET in the very near future. So there's one dimension, though, when we're talking about multidimensional that we haven't addressed, and that's the temporal dimension. And we have a long record of doing trimodal MR PET EEG. That's the 3 Tesla Siemens that you've seen, and we're well on our way to be able to do this at 7 Tesla also. So let's look at structural. I think we don't need to preach the converted here. This is an image from 9.4 Tesla postmortem brain, and you can see the beautiful contrast. This is to make the PET people jealous. This is what we can do with MRI, and we can do that at 7 Tesla easily now. This is an image from about 10 years ago, and we can do that kind of thing in vivo too. 7mm mapping at 7 Tesla, R2 star, QSM, local field. Beautiful images that are now, I'd say, pretty much standard. So let's put a tick in the structural box and have a look at what we want to do with functional imaging. So we've been trying to do layer-specific imaging for a long time. With our 9.4 Tesla, we were well on the way before the damn thing quenched. And we then moved the work over to 7 Tesla, and we're able to do layer-specific fMRI. How do we do it? I want to spend a little bit of time on this method here, echoplanar imaging with keyhole. Actually, I patented it in around the year 2000, so it's quite old, but I keep developing it further and further. And basically, it starts off by noting that most of the SNR in case space is here in the center, and actually all the resolutions out here. So acquire the solid line first, skip a few lines, acquire the next solid line, skip a few, and so on in the sparse region, acquire all of the lines of the keyhole, and then start skipping again. And you reduce the acquisition time. And you'll say, yeah, but that's just an overlay of a high resolution with the low resolution. We have that controversy in MRI, not really controversy, it's a simple discussion. And that's just to show it to you again in 3 steps. You save the data and then reconstruct. And I'm pushing this point a little bit because I always get questions from referees who haven't really understood what we're trying to do. So, color-coded white, black, green, keyhole in the center, and there's a real update rate. You need 3 shots in this particular example to acquire the whole of your case space. But there's an apparent update rate, which is the update rate for each keyhole, because you're going to share the information between them. And so as long as you are quicker with your real update rate than the bold response, you're still able to quite accurately measure the bold response. So I produce an animation to make sure everybody gets the idea. Color-coded green, red, blue, and the keyholes are in black. And so you start your experiment, first keyhole, then all the lines go in, you reconstruct an image, on you go. Third image, and you see the apparent update rate. And now when you do the 4th shot, you throw away the first one. So no overlay. Your information is being dynamically updated. And way back, when I had time to do real thinking, I did the first 1 echo sequence, and I thought, hang on a minute, throw in a 180-degree pulse, and you can do a spin echo version of that. And once you've got the spin echo version, you can then just do another grating echo version. So that's that here. When you've done that, you can throw in a few more 180-degree pulses and put them into loops and all kinds of things. And actually, we've done a lot of that work already. So we did a dual echo version. Those of you who know Maxim Zaitsev, the dual echo is part of his PhD. And then I carried on with looking at 5 echoes, simply putting a 180-degree pulse. You get 2 gradient echoes, 2 mixed echoes, and 1 spin echo. And we did some studies with contrast agent, and you can see the 5 echoes here, and you can see the uptake of the contrast agent quite clearly. And with those, you can go to your hybrid scanner. You get cerebral blood flow from both the gradient echo and the spin echo, cerebral blood volume. And up here in the right-hand corner is your FET image to give you the tumor extent. And of course, you can do vessel size as well because you've got contrast agent. And then I put the project on ice for a while. Oh, sorry, just one thing. Because you're going through K-space much quicker, EPIC is quite robust against distortions. This is EPI, I've forgotten. I think these are results from 3 Tesla. And you can see how the temporal lobes are distorted. This is a gradient echo, and this is EPIC. So it's quite robust. And then we came back to the sequence recently and thought, right, we've got a 7 Tesla. Actually, we were doing it 9.40. Also, 7 Tesla, and we want to do resting state. Why resting state? Because resting state is the low-hanging fruit. If you've got whole brain coverage, all of your neuroscientists will be very happy with you if you can do 7 Tesla resting state. And we wanted to be able to compare the resting state, of course, with task-evoked paradigms, and then various applications in young children and neonates. We didn't quite get around to doing the neonates because we wanted a faster technique with higher resolution, but then a smaller field of view, obviously. And we want to go to sub-millimeter. Sub-millimeter with whole brain. There are lots of techniques out there with surface cores and slabs that can do sub-millimeter, but that's not going to get you resting state. We need resting state, whole brain, sub-millimeter. And we need to get below about 0.7, which was when I made these slides about the state of the art. And we're looking at 0.5 millimeter whole brain coverage with 1 millimeter slice, or equivalently 0.6 millimeter isotropic. So how did we do that? Well, first of all, we needed to create space for all of the echoes. After the 90-degree pulse, we got rid of the navigator echoes for phase correction and put them in the external loop just to go. Oops. So before the water goes everywhere.
Oh, is it the water?
Yeah, it's yeah.
We'll get that.
So it's just.
It's okay. I don't think it will go there. So I'm sorry.
Sorry about that for disturbance. So we took out the navigator echoes, put them into a separate loop to create more space for reading the echoes. Allows much smaller voxel size compared to the community standard EPI. And we then basically, thank you very much. We basically threw everything we had at the sequence, partial Fourier, partial Fourier, and everything else that we knew we could throw at it to try and reduce the acquisition time. And we looked at the Siemens reconstruction as well, because one of the things, if you want to, and I'm sure you know this, if you want to get your neuroscientists excited, everything has to happen on the scanner. And we looked at Siemens reconstruction, and it wasn't really performing very well. So what we did was took a Siemens sequence, used our own reconstruction, and vice versa. And actually, our own reconstruction was working a little bit better with the Siemens sequence as well. So this slide was supposed to be animated, but somehow the animation's been lost. But you see the issue that you take out the navigators and just put them outside. And these are pretty much first results from the 0.5 millimeter in-plane 1 millimeter slice thickness. And you can see, like you, we have some very talented neuroanatomists in our institute. And we got one of them to come and have a look at these images and said, identify some things that you can see that we as physicists don't see. And she was able to, Nicola Palmeron, she was able to identify various structures in these EPI images. They're not structural, they are the EPI images that we're going to use for fMRI. As you can see, the image quality is rather good. And then we got the whole brain resting state networks. We looked at profiles across the cortical ribbon. And at this stage, we just wanted to see differences. Thank you very much. We just wanted to see differences as we penetrated into the brain. And as you can see from the profiles, you see that. And then we looked at a group-wise activation of the resting state networks just to make sure, just a sanity check, and everything checked out pretty well. So we just to emphasize, there are a few performance criteria regarding in-plane pixel size. We want to be the smallest. These are all the competitor techniques at the time, so a couple of years ago. Normalized in-plane field of view, we would like to be the largest, because we want to be able to get whole brain coverage. The volume of a single voxel, we'd like to be the smallest. And number of voxels per temporal volume, we want to be the largest. So we've got about 18 million voxels per temporal volume. So having set up the 0.5 millimeter protocol, we looked at the resolution just by eye. Functional profiles look quite good. We had to fiddle around and use our own enhanced image reconstruction software. Actually, we checked out the Siemens software, Siemens sequence, CMRR sequence as well. And with our reconstruction, both those sequences work a little bit better. And then we decided to start trying to do something with it. So we managed to get this illustration on the cover of Human Brain Mapping, less specific fMRI using EPIC. I don't need to explain this to you, why we want to do it. Let's skip that. So 3 Tesla, 3 millimeter voxel size, you're not going to get very far. So state of the art at 7 Tesla is about 1 millimeter, and then you're starting to get there, but you still need to push further. And with EPIC, we've got about 0.6 millimeters, and I think that's now, remember, we talk about voxel size and resolution, so without paying too much attention, I'm always talking about the voxel size, and then we have to degrade it a bit for the real resolution. So we're about at 0.6, and we are starting to get somewhere we think we can start to look at layer profiles. Evoked activity, this was just raising a finger, and you can see the activity very nicely on the cortical ribbon. And the profile, and this was very gratifying. You can see as you go from 0, which is a CSF, towards the white matter 100, you can see a profile. And then we want to do a further sanity check. We knew from the literature there's a difference between a motor task and a motor sensory. So finger tapping, motor sensory, and just raising your index finger, just the motor task. That the peak in layer 4 should extinguish when you do the motor sensory, and indeed you can see that disappearing. So we thought, great, we can do something with this. And before we started, we looked at laminar functional connectivity. Patricia Pais in my group just extended the standard methods to include for each entry here, the whole of the 6 layers, and to see where we go. She did some thresholding and produced the usual superficial to superficial layers, deep to deep, and so on. Interestingly, and then she extended it further. instead of looking at one correlation value for each pixel or region, she introduced a pseudo temporal dimension by splitting up the time course. I'll just skip that. Using a kind of like sliding window to see what's going on with the connectivity. So you've got outer to outer connections here and inner to inner down here. Let me just play that for you. You should be able to see that fluctuating. I thought, ooh, what's that telling us? Don't know. K-means clustering, and it turns out from these data, and they're very preliminary, that the brain's spending most of its time in two states: superficial, and deep to deep. And she came up with this dynamicity to look at laminar connections and see if these can be biomarkers of brain state changes and whatnot. And we had a study going on in the Institute on depression patients. We thought, oh, let's just add this sequence and see what we get. So we did a group of healthy controls, prevalence of state 1 versus state 2, about here. And we did a group of depression patients, and we retrospectively divided them into responders and non-responders. And the therapy was talking therapy. It turns out that the responders, the fluctuations went back down towards normal levels, and those people that said, nah, talking didn't help me at all, carried on increasing. This is really a work in preparation. We're still trying to gather more patients to see if this is statistically significant, and hopefully in preparation, hopefully we'll be able to submit it soon. So it seems to be useful. So let's put a tick by functional. We can get towards layer specific, and with people who have 10.5 Tesla and 11.7, this should be easily reachable once the hardware is under control. Now let's come to the focus of this workshop and how our work fits in. We've been doing metabolic imaging for many years, particularly sodium. Actually, with my background in solid state physics, density matrix calculations, and so on, multiple quantum filtering of sodium. This is just what I love doing. And as you get to 7 Tesla, you've got just about enough signal to start filtering and throwing stuff away. And then oxygen, deuterium, phosphorus, these are all things that are amenable at 7 Tesla, and they're all metabolically active nuclei. And of course, let's not forget the PET. So we developed a method, again, based on EPIC for rapid measurement of oxygen extraction fraction. The sequence, so we went from 5 echoes to 10 echoes, so we just put another 180 degree pulse in and increase the sparse factor from 3 to 7. And what we're getting now is T2 star, T2, and then we can calculate T2 prime. As you know, if you have T2 prime, then you can get at the oxygen extraction. There are other methods that exist, but they're very slow. And the goal of this work was to be able to look at stroke patients 1 minute and be able to say, in wake-up stroke, to be able to try and determine when the stroke occurred. We're not quite there yet, but we're making progress. And we're lucky to get 1 minute with these stroke patients. And we need rapid imaging. And, you know, time is money, so let's move on. Make it multi-contrast and quick. And other methods use a number of sequences. We wanted to have all contrasts in one sequence for fast acquisition and to get at the OEF. So when we're talking about metabolism, of course, oxygen is critical. And if you can get a handle on OEF, and in fullness of time, if you can measure the blood flow, then you've got CMR02 as well. And we're first, I think it's not exactly low-hanging fruit, but it's a lot easier than having to try and measure blood flow at the same time. So this is what we're trying to do at the moment. PET's the gold standard for this. OEF is proportional to R2 prime, and if you can get, as I mentioned already, T2 star and T2, you can get that. All the other parameters are just constants or to calculate the OEF. I'll just skip these. And so we can get the 10 images from one sequence, 2 gradient echoes, 2 mixed echoes, 1 spin echo, further 3 mixed contrasts, 4, sorry, and then a second spin echo. Now it's important I do a lot of quantitative MRI as well, and I want to test everything in phantoms. And if you're going to do fitting, 1 spin echo is really not good enough, especially when you're in a noisy environment. 2 is a minimum. So we're there, we've got 2 spin echoes to give us the T2, and then enough gradient echoes to get a good T2 star. So previous methods limited by low resolution, number of echoes or images they're requiring, 5 to 7, only 1 spin echo, longish echo time. We've improved on all of that, so high resolution, 10 images, second spin echo, and we've reduced from about 120 to about 114 for the second spin echo. 20 slices in 57 seconds. So I think talking to a radiologist, neuroradiologist, they might give you a minute on the scanner. I mentioned my background in quantitative MRI. First thing I do with a new sequence is do a spectroscopic measurement and test. That's on the this side. You can see the spectroscopic values in green, reference imaging method, and then our new sequence here. And the agreement is pretty good. Did a small cohort study, also looking pretty good. Thought, right, how do we convince ourselves that this sequence is working? Got a graduate student that learn to hold your breath for 60 seconds. Wasn't in your job description, but learn it anyway. And then we're going to put you in the scanner. So we put him in the scanner and told him to breathe for 60 seconds, hold his breath for 60 seconds, and so on. And you can see mean of all slices is the blue. A representative slice is in orange. And you can see it's very, very easy to see the changes in OEF. Now, what we want to do is not do a mean of all the voxels in the slice. We want to go to regions and then eventually single voxels. We're working on that. But if you just look at the slope of that curve, for example, it's really easy to separate out when the person was breathing and when there was breath hold. And significant differences. So goal is voxel by voxel with high temporal resolution, 20 slices or so. Our baselines agree with values in the literature, particularly PET, and proof of concept breath hold. Admittedly, it's quite a stark modulation of OEF, but still, if you couldn't pick that up, go back home, start again. So I think we're ready to start using this. The sequence has been installed on a 3 Tesla Prisma in a clinic, and we're now just trying to get regulatory approvals from the ethics committee so we can start using it. So we've ticked structure, we've ticked function, we've got first part of metabolic imaging with OEF, but now let's have a look at where the real meat is, so to speak. How can we do hybrid MR PET at 7 Tesla And please don't misunderstand me. I'm not talking about clinical applications of MR-PET. I'm talking about neuroscience, clinical science. We are fortunate, as are you, that we don't really have to worry too much about patient reimbursement. We want to do science. So now imagine you've got your 7 Tesla MR-PET. You can do, just off the top of my head, FDG PET to look at up to where the tracer gets trapped. You can do deuterated glucose to look at downstream products. You could build double tune coils, do functional fMRI with protons, FTG, and deuterated glucose. Or you could say, no, I want to do phosphorus at the same time. Now suddenly it's really opening up if you can do that at 7 Tesla, because at 3 Tesla, doing X nuclei is a real challenge. At 7 Tesla, you really now, I'd say you've gained your passport, your entry ticket to this wonderful playing field. The work has been led by Christoph Lescher. I was the coordinator of that grant and responsible for the MR part. We had people from Aachen University and also Monash in our collaboration. And Siemens very kindly provided us with crystals. So we started looking at the 3 Tesla that we have. It's the insert, not the scanner that you have. Spatial resolution about 4 millimeters at center, 6 at the edge. Limited field of view about 20 centimeters. Sensitivity around 2%. And that's what it looks like. I think most of you have seen it. That's the standard clinical, and this is the BrainPET. So I was going to say we're a bit better than that. 3 millimeters or so higher sensitivity, and it sits inside a trill. We're still using it for actual clinical work. The idea was then write a grant, got the money thankfully, 3-layer scintillator, 8-channel dipole transmit receive array, which we needed to make PET transparent, digital silicon photomultipliers, and a gantry that was strong enough to support all that, so it could go inside the bore of the 7 Tesla. And it's quite heavy. Crystals are quite heavy. So we had to take care of the patient bed. There are a few photographs of what it looks like. Again, I quite like the detail. Connectors for the alarm ball and the headphones are here. And you can see it being put together over there. The design for the RF core that we went for is a J-pole antenna array. Nice thing about it is that you can shift all of your lumped elements out of the field of view of the PET. So basically, this is just a very thin copper tape, and all of your electronics sitting over here. The performance parameters for the second generation were, we wanted to cover the whole brain. Cerebellum is important. There's even a journal called Cerebellum, so it must be important. Sensitivity, we wanted to increase the sensitivity, so greater than 12%. Spatial resolution, we wanted to be below 2 millimeters. Timing resolution below 500 picoseconds, and we wanted compatibility at least up to 9.4 Tesla. We've done all of that. And I'd like to show you some of the results. So this is again just a few more pictures. That's what the crystals look like. That's the gantry completed. The cassettes with the cover off, water cooled. That's the PET transparent coil with its shield, and that's it sitting on its gantry, on its trolley. First, brain phantom images, no normalization, no scatter correction, no randoms correction with attenuation correction. You can see that's the phantom. We got from a colleague of ours many years ago, Hidehiro Ida, and you can see the quality of the PET. We then ran the MR. We wanted to see is the MR side of things being influenced with the BrainPET running. That's turboflash of the brain phantom EPI sequence, and then just stuck a few bits of fruit into the scanner just to see something different. So that's all running. Again, just to show you the PET images in a bit more detail. Those are the parameters for the acquisition, reconstruction with our own Presto reconstruction technique, and resolution. So we took this phantom, put it into the scanner, reconstructed with Presto, and you can see these are the 1.6 millimeter rods, and I'd venture to suggest you can just about disconnected on the projector. Okay. Something happened. I don't know. I'm sorry. You can see the 1.6 millimeter rods here, and I'd like to suggest you can just about resolve those, and that's without any corrections at all. Comparison with other scanners, this in yellow is what we've built. 3-layer geometry, resolution, let's call it 1.8, but I think once we've done all the corrections, we should be able to get to about 1.6. This is the 3 tails of the insert that we have, NeuroExplorer, which is not MR compatible, but has a similar resolution, and another BrainPET for 7 Tesla that I haven't seen images, but Christoph assures me there is another one. So this is just to show you the phantom in a bit more detail. And I think here you'd agree that you can just about resolve those. I got these images by email last night. So brain phantom fused, there's the PET, MR, and fused images over here. I don't think this is saying very much, but it at least shows you progress is afoot. Thank you very much. I forgot my acknowledgement slide, but I'd like to thank, this is real teamwork of the whole institute in various ways. I alluded to Siemens donating the crystals to us, and I'd like to thank you for your attention. Thank you.